Okay, so I'm Eric Maglio, and the topic of my talk is the F35B as a quad plane. This is a project I've been working on for a number of years. There's some other talented people all around the world that are working on similar projects, but the big differentiator with mine is that mine works. It flies the whole flight profile rather nicely, and it works because of ArduPilot. So I'll give an overview of the airplane in general, but I'll also go a little bit deeper into some of the customizations that I made to ArduPilot to fit this particular fairly unique configuration of aircraft. We had a good day at the flying field yesterday, and the winds were low enough to sneak in a flight. But if you weren't able to see that, I've got a video clip here that I'm hoping to show, if the hotel Wi-Fi is permitting. There we go. This is there's not many aircraft where you can fit an entire flight into one slide of a presentation. This is one of those. I don't know if that's a feature, but it's worth doing at least. So really quick takeoff and transition into forward flight. It's consuming about 3,000 watts to get off the ground. So you really want to get into fixed wing mode where you're a little more efficient as quickly as you can and save some of that battery power for the landing. In the fixed wing flight, it's almost always in fly-by-wire A. I've got the bank angle limits turned up, of course, but it's pretty comfortable to fly in that mode. Checking some control responses too. And then back into the hover. This was the first flight of this particular model in this video. So I had the multi-rotor tuning done, or at least done to an extent where I could fly it, but that was the first real fixed wing flight without any change from some default tune. A retractable landing gear, of course. Quite a lot of yaw authority with the vector thrust in the tail. All right, so we'll dive right in here and just go into an overview of what this aircraft is. It is, of course, in real life, a VTOL-capable jet fighter. That's vertical takeoff and landing. Most of the time, you'll see it do short takeoffs with some roll, just because it can't really carry any payload if it's got enough energy to vertical lift. But the concept is the same. But naturally, all of aerospace engineering is a compromise, and when you're starting to get aircraft that do multiple different roles, you're just stacking compromises. Very inefficient, very low performance, but it's really cool. And because of that, it's worth building a model of for sure. Now, the configuration of the full-size aircraft, there's, of course, a turbofan fighter jet engine. There's a forward lift fan. That lift fan is two counter-rotating fans, and it's shafted to the main engine with a clutch. So there isn't a separate power plant for vertical lift, but the thrust from the lift fan can be varied a little bit with some inlet vanes, with some nozzle vanes, so that they can achieve pitch control that way. Roll control is done with roll posts in the wings. These are compressor bleed. So it's air that comes not from behind the fan, but behind a few stages of the compressor. That'll be important with how it translates to my approach in a bit. Now, if you squint, if you look at this closely enough, that's a quadcopter. It's a plus mode quadcopter. Where that compressor bleed comes into play is I've made the decision on my model to use fans for roll control. When you're bleeding from a compressor, that's high pressure air. It's low velocity air. So you can move that through ducts. You can make thrust with nozzles, and you don't lose a lot of energy that way. But when it comes from behind a fan, if I were to take some ducted exhaust behind the main fan here, that's lower pressure air and it's higher velocity, and it's really lossy. You're going to lose energy every time it goes through a bend, or just based on viscosity from the walls of the ducting. And I had a couple of test aircraft where I could use that, but it just didn't provide enough authority for being outdoors, having all this surface area affected by wind. It wasn't the way to go. So the roll control with the motors is an interim step. I do plan to hide that a little bit better with still dedicated fans, but ducted elsewhere inside the aircraft. But that's how it was necessary to configure this to get it to fly. The next major step is the motor mixer, and it's a plus mode quadcopter, but it doesn't use variable torque for yaw, especially with two different sets of very different power plant. In fact, the roll thrusters are not contributing meaningfully to the total thrust of the vehicle. They're just there for roll. And so my first thought was to take the plus quadcopter frame and add the tilt servo code from tricopter, but that turned out not to be the right way to go. There's a lot of code necessary for the yaw tilt to work, and it was much easier to take the tricopter frame class and just add that fourth motor back. You don't even have to change the motor number, because on a tricopter you have 1, 2, and 4. So in fact, it's possible to get this configuration to fly with not a lot of important features, but fly in general with 12 lines of code changed from stock ArduPilot. And that's a lot of my very early first hovers were that small of a change. I didn't even bother to rename the tricopter frame class that early. It was just tricopter with 12 lines of code added to it or changed. And then, of course, it's not really a yaw servo like a tricopter. It is a much more complicated arrangement of 3D printer parts. So I'll talk a little bit about the 3BSM. The acronym stands for 3 bearing swivel module. And I've had a couple of questions asking, is this how the F35 really does the vectored thrust? And the answer is yes. This is largely a realistic configuration. The tilt range, the vector range is pretty close to the real aircraft. They are not using 3D printed plastic, but this design works well for this model. It has 48 bearings, it has 85 screws, and there's a 105-degree range of motion. So I can have thrust in the backwards direction for braking and for translating backwards. I, of course, can go all the way to 0 degrees of deflection for forward flight. And then one of the three, the section there that's planar, the planar ring, that will move for yaw control. This originally was powered by some gear motors with encoders, and that worked for a little bit before generating some reliability issues, and then I landed on the CAN servos from Hitech. With servos, you get a little bit more quality control on the motor itself, and the gear train to a lesser extent as well. And that was really important for this. The gear motors had a failure mode where you'd burn out brushes and you'd lose torque without too much warning. So you'd run into situations where you're flying and suddenly your thrust vector becomes fixed, and that's not fun. To drive the CAN servos, there's a custom control board running custom software. I'll talk about that in a little bit as regarding why that's necessary. But the main takeaway is that it just uses simple PWM inputs. As far as ArduPilot is concerned, this is a tilt servo and a yaw servo, and all of the complexity of the nozzle motion and the trigonometry to do the circular movements of the rings, that's all abstracted by that controller board. So here's what I mentioned about that custom software. The high-tech CAN servos are unique in that they don't have any stops, so they can rotate both in continuous revolution mode and have encoder feedback for position control. And in the proprietary CAN protocol, there is a message for specifying integer numbers of rotations and encoder positions so that the servo can rotate anywhere from 0 to 32,000 continuous revolutions with full position control everywhere in between with one CAN message. But that's only supported in the proprietary, the CAN 2.0 protocol. It's not yet in drone CAN, and that's what forced me to use a custom board in between, just doing that abstraction between those PWM tilt and yaw servo inputs and the CAN 2.0 message that allows me to achieve that. I don't need 32,000 rotations, but the two main off-axis rings in the nozzle, the way that they're geared, need about 4 full rotations to accomplish the full range of the thrust vector. So it'd be really nice to eliminate the need for that. I haven't found a way to do that just yet. The custom solution works. So I'm sticking with that for now. I made a neat little configuration tool for setting up things like the servo speed, homing procedures, PWM input ranges, just some parameters that are specific to that nozzle controller. But if I can move this functionality to Lua scripting or something similar, then I can just delete this extra hardware, delete the extra software, save some weight and complexity. And that's on the table for next steps for this. There's a couple of ways to do that too. One might be supporting the arbitrary CAN protocol that the high-tech servos support. Another might be supporting arbitrary CAN messages in Lua that aren't necessarily drone CAN. Or maybe even a firmware change to the servos themselves that would allow the -1 to 1 abstracted rotation range to actually be multiple rotations. And then you'd configure the actual travel limits that you wanted in the servo and not in the flight controller. So there's a few ways to do that. Not sure where that'll head, but probably one of those. So next, I'll go into some of the airframe development steps that I took. This was very iterative. I had a lot of models that I built, a lot of stepping stones in between, things like that. The first model was just essentially a quadcopter with a foam airframe around it. I couldn't transition. It didn't have any control surfaces. It couldn't even tilt the motors. But this was what I used to test my changes to the tricopter frame class. And then eventually when it became my own frame class with the 4 quadcopter layout motors, but with vectoring for yaw tilt instead of changes differential torque. The next step was to actually build that 3-bearing swivel module, use ducted fans, and then assemble that on a frame that I could use to test the power system as a whole. And that's where a lot of the iterations on the 3BSM happened, where I figured out that I needed to go from the gear motors to the servos for more reliability. And then this is also where I developed some code to change how the vehicle translates back and forth when it's hovering. It did actually run quad plane, so you could flip into fly-by-wire and it would transition and it would not go very well without the wings. Yes. So that was next. I slapped some wings on that frame, just foam board wings around the wooden spars, so that I could do transitions, forward flight. Of course, there's nothing new in the forward flight. It's just, it's a rather draggy aircraft. Just tuned it in fly-by-wire and dealt with it. And then it spent, I think, about a year, maybe more than a year in that configuration, because really, aside from the shape of the airframe, that has all of the functionality that it needs to have for this project. And then lastly, when that was flying reliably and I was fairly confident it wouldn't crash, I integrated everything into a cooler looking airframe that was more recognizable as an F-35. And that way I didn't have to explain to people why this doesn't look like a fighter jet. So that's the iterations that I went through. In general, of course, this one probably crashed 2 or 3 times. This one crashed 2 or 3 times. So there were, permutations in between, but that's the general overview. There's also real flight models. I had CAD for both of those aircraft configurations, of course. So I was able to get those into a mesh format that I could ingest into real flight. And then, of course, ArduPilot running CITL, even with my custom branches, can fly these aircraft in the simulator. And very realistically, in fact, a lot of the handling and the tuning is pretty close between the real flight models and the physical ones. I spent a lot of time trying to get the mass properties in the real flight model editor just right. So this was a really good way to validate code changes and scripts. I'm not really a software developer in general, so a lot of times when I was making changes to the code, I needed the extra confidence from testing in the simulator in order to make sure that I haven't broken anything important. They're also much easier to repair than the real models. Like bashing the spacebar hasn't managed to ever put this thing back together. So that's nice for sure. It also comes in travel size. So you've noticed this model is not necessarily the same as that first video that I showed and some of the pictures. This is a scaled down version, and you can see the size difference between the two models here. 70 millimeter ducted fans instead of 90 millimeter ducted fans. And this version exists pretty much only for this type of event, where I can pack it in a case and bring it somewhere, show it off, talk about it, that sort of thing. It's pretty much the same design. Almost all of it is just directly scaled down, and then the removable surfaces are added so that it's easier to travel with. Here's a few more details about the airframe. Even though it's a step above that test bed with the wing strapped on it, it's still stand by.
We're still getting it through.
Okay. Might be a cabling issue.
Yeah.
It's still designed to be a pretty simple airframe. It's just foam board. Is it over there?
I haven't got the whole thing.
Yeah. Sorry.
Good now, right?
Okay. You guys can edit that out before it goes into the. We'll fix it in post. Yeah, so it's foam board and some carbon fiber and some tape. It's not good.
Needs to be the one against the wall. It's a bit loose.
All right, nobody breathe for the next 20 minutes. So it's flat foam pieces. It's got carbon fiber spars. These are the structural elements that interface the removable wings as well. So the wing panels will have a tube that inserts into this square spar. And then all of the important bits, motor mounts, landing gear mounts, also clamp to those carbon tubes that run the length of the fuselage. What to do about that? It's got a smaller 3BSM. Printed from lightweight PLA instead of regular PLA. Fewer bearings and fasteners. Just gonna sit over here and see if I can. Is there another way we can project to the projector? Can we just HDMI?
Yeah, probably a new cable.
Okay. Yeah, and then all of the white components that you see, the round parts of the fuselage, mounts for the vertical tail, those are also lightweight PLA. So it's an interesting mix of material that keeps it lightweight, simple to build, easy to repair, and then of course, easy to transport. And I had a custom case made so that I could bring it on trips and it would endure the rigors of baggage handlers. So now I'll dive into one of the issues that needed some customization to solve, and that's body tilt. So if you've built a quad plane before, if you're in a Q mode, if you're hovering and you command a forward or backwards translation, you're going to get pitch upward or downward of the vehicle, which is great for multi-rotors, but for a quad plane, when you're driving a big wing around, and that wing is subject to aerodynamic forces, now you can create lots of downforce, you can create side forces if you're pitching that wing around. And if you're in a power-constrained aircraft that has tiny ducted fans, that can really make or break whether you can fly reasonably well. V-forward gain does not help this. It doesn't fully inhibit the ability of the aircraft to pitch. It just assists with the forward velocity demand. So here's a vehicle in real flight, just showing how difficult it is to translate back and forth if you allow the vehicle to tilt. And even in the simulated environment, you can hear if you start moving fast enough forward, the lift system will saturate. They can no longer overcome the downward force from the aerodynamic surfaces, and you'll just get driven straight into the ground at full power. So that's something that happens in real life. It happens in real flight, and it needed to be fixed in order for this to be something that I could fly around confidently. So how can we fix that? Turns out the loader controller doesn't really care about the pitch angle of your vehicle. It cares about the angle of your thrust, and is only using the body tilt because that's the method that it has available to influence where that thrust angle is headed. So the F-35, we have all of the tools we need to know the thrust vector angle at all times, because the 3BSM is what's manipulating that. So I used a bit of vector math to come up with the relation between the 3BSM tilt angle and the total thrust vector angle, because also we of course know the distribution between the thrust component from the main fan and the lift fan. And like I said earlier, I'm pretty much ignoring the contribution from the roll fans to the total thrust. They're not really important for this math. And then I locked the pitch level, at least in Q loiter mode, and then allow the output of the loader controller to, instead of demand a pitch angle, demand a 3BSM deflection that produces the same amount of thrust vector angle. So now you get this. Makes it much easier to fly around. It's not putting extra stress on the lift system. It also works backwards, and it just looks a lot more natural, really, for any quad plane, not just the F-35. The backwards tilt is especially cool. The nozzle can go to 105 degrees, like I mentioned earlier, so we get 15 degrees of backwards deflection, which is enough really to get moving quite quickly in reverse. Okay, so this doesn't solve quite everything. It creates a couple of new issues. One of them, that 15 degrees of backwards tilt is, while it's enough for moving around like that in the hover, it's not really enough for braking during transition. And it's equivalent to setting a Q angle max of less than 8 degrees. Because since there's only one global setting for Q angle max, you can't specify, hey, you can only go 8 degrees backwards, but you can have 30 degrees forwards. This is limiting for the performance of the vehicle in general in hover. So if you ever get compelled to take a quad and set Q angle max to that, you'll know what I mean. Very lethargic. And the other issue here is that when you're transitioning back into hover and you've chosen to lock the pitch level, it immediately unloads the wing. This doesn't really have an airfoil. It's just an approximation. It doesn't make much lift at all at zero angle of attack. So that'll saturate the lift system really quickly. ArduPilot does a great job of taking that load and recovering, but it'll lose altitude in the process. So that was about 10 or 20 meters of altitude loss during the course of the transition, just because the amount of lift being generated by the wings that got dumped couldn't get picked up that quickly by the ducted fans. And the deceleration is pretty lethargic as well. Even though it's a draggy airframe, it's not making a lot of drag when it's flat. So that's quite a lot of space needed to slow to a hover. So the solution to that is to allow some body tilt again, but only in the positive direction and only when we've exceeded the amount of thrust vector angle demand that the nozzle can produce. So there's two steps to the like a reverse velocity demand now. First, the nozzle will move to the negative 15-degree position. And if you're still demanding more, either in a transition or manually, it'll start to allow upward pitch of the nose. And there's just a little bit more vector math to do that. It gets a little bit more complicated, but we still have all the components of information that we need to determine this and establish the right relationship between the loiter controller and the 3BSM. We just now have two components that are contributing to the angle of our thrust vector instead of just the one. So here's a clip of the results. The lift from the wing is now maintained a lot further into the transition, and it bleeds off more naturally with airspeed instead of just immediately with pitch. There's more drag as well. And now that Q angle max really can be set to any arbitrary number because we're no longer limited in the reverse direction. We can just allow some pitch up. We were never limited in the forward direction because the nozzle can go all the way to level. And then we weren't limited in roll either. So I chose a setting for Q angle max that resulted in the small positive pitch angle that the aircraft will allow when it's got a maximum demand being a reasonable angle of attack for the transition into landing. You get a really nice, much better braking, much shorter transition in that case. So very brisk stop, looks a lot more natural, doesn't lose any altitude. Certainly helps. All right, so now I'll go into some next steps, what I have as far as hopes for the future of this project. From a software perspective, I'd really like to get that multi-turn servo functionality away from the custom software and the custom hardware. So I'd like to investigate some of those potential, not necessarily workarounds, but improvements to DroneCan or the servo firmware to allow that. I'd like to replace the frame class with Lua scripts as well, and then perhaps also those customizations to how the loiter controller works. Stand by here. Mostly because it's a little bit cumbersome for me as not a software developer to maintain that custom ArduPilot branch. Usually when it gets behind even stable releases, and then when I go to rebase it, it causes me more headaches than it would perhaps cause many of you. And then, yes, also the thrust vector based longitudinal control. That I hope to convince you guys that it's useful as for quad planes overall, not just for this project. And then maybe that can work its way into being a proper feature of ArduPilot. Some more specific things to this particular airframe. You may notice that the full-scale model or the full-scale aircraft will droop the control surfaces and hover. It'd be really cool from a realism perspective to emulate that. And that's probably something I can do with scripting right now. And then to expand upon that, a short takeoff type of flight mode, or at least modification to parameters in an existing mode that would allow rolling takeoffs with some nozzle deflection. That would just dial up the realism quite a bit, and I think it would be really cool. On the hardware side, I'm moving towards my final vision for the airframe, which is a larger model, fully contoured, nice scale appearance, and built entirely with 3D printing. So it's a 110 millimeter ducted fan instead of the 70 that's in here and the 90 that's in my other model that was in the video clips. And the size difference between this and the larger of the two existing models is about the same as the difference between the larger model and this. So it's about 40% larger than the one that you're seeing here. It'll be quite big. And you can see that I've got the outer mold line just about finished, and I'm moving on to structural design for all of the internals that are needed for a 3D printed airframe to be strong and lightweight. And I've got the upscaled 3BSM done as well. So that's about it. That's where the project is now and where it's headed. And if you guys have any questions, fire away. Rich?
So on the integrated the longitudinal, definitely look for the tilt vectored footlights, the ones that have like the two front tilting rotors that are very clear about it. And so yes, very much like to integrate that. We'll have to discuss more about the SLTs, the separately thrust. Obviously, they can only provide forward thrust unless they've got a reversible motor. And so that's a little more limited.
Right.
But I think at least for the tilt vector ones, I think it's, yeah.
Yeah, absolutely.
Operate.
Bill and I are working on a generalization of the multi-rotor code that will directly support a lot of these things that you are dealing with or had to hack around. So hopefully there will take some time for that to mature and get in, but yeah, this has been the types of issues you've been dealing with have been plaguing the quad plane community in particular, but also some of the more creative VTOL vertical takeoff aircraft as well. So yeah, so hopefully in another year or so you'll have a bunch more tools that make this a hell of a lot easier.
Great. Looking forward to that for sure. There, Matt.
Resolving the thrust vector, I assume what are you asking for the rear thrust vector, and then how you're resolving how that's in terms of like the apparatus.
Okay, so the question is, how is the thrust vector output being resolved internally? The actual thrust vector angle from the 3BSM is pretty much linearly scaled around the PWM output to the tilt servo. My software that's on the custom hardware that's on the 3BSM controller runs that abstraction and makes sure it's linear. And then aside from that, the output of the loiter controller already is a thrust vector demand. So there's just a little bit of trigonometry involved in taking that thrust vector demand and translating it into a tilt servo output PWM value that corresponds to the thrust vector angle that I need. Robert?
Now, earlier on, you said that you eventually want to take those roll thrusters and internalize them. Do you have any idea how to do that yet?
Yeah, so the question is, how will I get away with hiding the roll control motors? So right now they are, it's a very thin wing, and they're the smallest propellers that I can get with enough authority to achieve roll control. The larger model that I mentioned is part of the solution to that. I really need to go up in scale in order to have any feasible way to hide those. But what the solution I think will be is a small ducted fan instead of a ducted propeller buried in the fuselage with exhaust ducting out to the underside of the wing. And I think at the larger size, I can get away with that and not have too many losses eating away at the roll authority.
Not the subject of thrust losses, so when you go from horizontal to the vertical, was that like a 15%, 20% reduction in thrust with the ducted fan, or was it end up being?
That's a good question. So it's how many losses in terms of thrust does the tilting of the 3BSM involve? And it's less than I expected. It's between 5 and 10%. And I was able to find that just by looking at motor output balance between the lift fan and the main fan, because I know where the CG is, of course, relative to the two, and they're the same power system. And there's some weird flow interactions that happen with the 3BSM. Actually, vertical 90-degree vertical deflection of the nozzle results in a thrust vector that's a little bit backwards, a few degrees backwards. So there's some flow bouncing around and redirecting inside the nozzle that's not quite straightening out all the way. So there's a handful of weird quirks like that I've encountered.
The anticipated lower bandwidth from the nozzle and the port pass direction, did you have to lower, I'm assuming you have to lower the Q where it needs quite a bit. Except the port the ones in there.
That's a good question. So it was the question is how did using the nozzle control instead of body tilt affect the tuning of the loiter controller? And it is a very slow actuator. It's a nonlinear actuator. So the speeds that you can get for thrust vector angle change vary based on where the nozzle is at that moment in time. So it's definitely weird, but I haven't yet changed the loiter gains at all. It's flyable. It's reasonably responsive. I'm sure there's a lot of room for improvement. But so far, since the loiter controller is it's still getting what it's asking for in terms of thrust vector angle. It's just coming from a slower actuator. It probably just behaves like a vehicle with a lot of inertia would behave. So reasonable, not ideal, but flies. All right, looks like that's it.
So big round of applause for Eric.